Hello and welcome to another read along in geometry. Today we are reading through section 2.4, three-dimensional shapes. This is where it really gets exciting. First, our applied problem to set the stage. A restaurant packages takeout food in cardboard containers like the one shown. The box shapes are convenient in that when assembled, they stack inside one another. They also can be unfolded and laid flat. If you ignore the flaps to hold the cover shut, what is the shape of the box when unfolded? Unfolded, okay. So you take that shape and peel it apart to get now back to a flat shape. That transition between two-dimensional and three-dimensional is always interesting. So, first up, some new terms. Polyhedra. Thus far, we have been studying figures and regions on the plane. That is, figures that are zero-dimensional points, one-dimensional lines, and two-dimensional, such as triangles and the other polygons. All right? Anything you could draw on a sheet of paper. Now we begin a study of three-dimensional shapes. Right? And this makes it much more difficult to truly draw on paper. A polyhedron, plural polyhedra, is a three-dimensional shape composed of polygonal regions, any two of which have at most a common side. Okay? So you're taking two polygons and connecting them together. I wish I had there's all kinds of toys that do this magnetically and can attach themselves, right? And you can build a 3D shape out of that. In addition, it is an enclosed, connected, finite portion of space without holes. Okay, so we've got kind of two halves of a definition here. So it's both three-dimensional shape made of polygon regions, which have at most a side. That is to say, they're not, on top of each other. And it is an enclosed, connected, finite portion of space without holes. Okay, so I have some 3D, you can see the example pictures there. I have some physical three-dimensional polyhedrons here. So here is an example of a cube. You can see that rotating now. I can move it in 3 dimensions there. And they say without holes. So if I was to, take off the center here, and I don't know if you can see that because it's kind of translucent, but there's a hole there, right? I can stick my finger in here. And now, with that hole there, it no longer counts as a true polyhedron. Okay? Donuts don't count. All right, the polygonal regions of a polyhedron are called faces. The common line segments are called edges. Okay, so where the faces meet, you get an edge. And a point where edges meet is called a vertex. Okay, faces meet to create edges, and then edges meet to create vertices. So you have a face, edge, edge, and vertex where the two edges meet. Vertices are the same as vertices are the same as the vertices were on the polygon. Okay, now, two common types of polyhedra we will study are prisms and pyramids, probably the two most common. A prism is a polyhedron with two opposite faces called bases that are identical polygonal regions in parallel planes. That is, planes that do not have any common points. Okay, that's important. Two opposite faces, we call the bases. Identical polygonal regions that are parallel, okay? So two identical parallel polygons, and then they have to be, connected, of course, to create the full enclosed three-dimensional shape that is the polygon. All right, the other faces are called lateral faces. So you can look here at the rectangular prism. So we've got two identical rectangles. All right, they are parallel to each other. This flat side here on the top and this flat side here on the bottom, if extended infinitely in all directions, they would never get closer or farther apart. They will never intersect. And then they're connected by all the lateral faces here. Okay. And similarly, we can have a triangular prism. Here is a three-dimensional object there. So we've got the triangular bases here and here, on top and bottom, left and right. You can orient it any way you like. And then between those two are the lateral faces between the two matching bases. With a rectangular prism, since every opposite rectangle, this and this one and this one, right, or front and back, they're all going to match. You can technically call any of them the bases, and the others become the lateral faces. Doesn't make a difference. Okay? And then same there with the hexagonal base. I don't have a hexagon piece. Now, did that get, oh, let me highlight that, right? The other faces are called lateral faces, and the height of a prism is the perpendicular distance between the bases. Okay, notice it has to be perpendicular. We'll get to when that isn't in a moment. Prisms are named by the shape of their bases. Some examples shown below, right? So whatever the base is, whatever the two matching opposite parallel faces are, that's the name, and then you turn it into an adjective. So triangles becomes triangular prism. And there's one other thing we can do to prisms. We can slant them. Prisms whose lateral faces are rectangular regions are called right prisms. Okay? The lateral faces are all rectangles. They are right prisms. And you'll notice here in this diagram, as well as all of my shapes there, every angle between two faces, interior angle in here, right, is going to be a right angle. Not just the rectangle itself, but between this side and this side, they meet at right angles. Even on the triangle, right, between a lateral face and the base, okay, is a right angle. Otherwise, they are called oblique prisms. Okay? So oblique prisms would be, their lateral faces are non-rectangles. Okay? So they didn't type that out, so if you want a definition to write into your notes, you'd say an oblique prism has non-rectangular lateral faces. Okay? Most commonly, they'll end up as parallelograms. Okay? As you can see this one here. And this is what happens when you take it and you squish it, right? Which mine are all hard plastic. I can't do that too, but you can imagine any of these could be slid, right, and slanted over, and you get an oblique prism. Notice these faces are still parallel. I can shift them relative to each other, but they don't get closer or farther away. Okay? Nor do they twist. All right? Twisting will result in a different shape that we're not covering in this section. All right. Next up, pyramids. A pyramid is a polyhedron consisting of a polygonal region for its base and triangular regions as lateral faces. Polygon as the base and triangles as the lateral faces, which all meet at a point called the apex of the pyramid. All meet at a point called the apex. Okay? Sometimes this is called the vertex. Okay? But that can get confusing because every corner where faces meet is a vertex, but we want the best vertex of all of them called the apex. And typically you would build your pyramid such that the base is on the bottom and the apex is the highest point. All right, the Egyptians were very good at this. The name of a pyramid is determined by the shape of its base, as with the prisms, and the perpendicular distance from the apex to the base of a pyramid is called the height of the pyramid. Perpendicular distance from apex to base. Okay, so there you have apex. The height now goes inside the pyramid into the middle of the base, and that one is a equilateral triangular pyramid. So I have one here. So here is my equilateral triangle, and here are my triangular faces that meet at the apex there at the top. And the height would be perpendicular between apex and base. Okay. Notice the oblique pyramid that we have here, our hexagonal one, is looking kind of funny here. Okay. When the base of a pyramid is a regular polygon and its lateral faces are isosceles triangles, the pyramid is called a right regular pyramid. Okay, regular polygon and isosceles triangles, you get right regular pyramid. If the lateral faces are not isosceles, the pyramid is called an oblique regular pyramid. Okay? Any other type of triangle, you get oblique. Remember, of course, the equilateral also count as isosceles, so this literally leaves us only with scalene as a possibility. And we can also talk about the slant height of a right regular pyramid is the height of any of its faces. Okay? The slant height of an oblique pyramid would be different per face, and so you can't really say that this pyramid has one slant height. But we can imagine, if you will, the proper height of this pyramid would be measured down to some point that is here, still a right angle with the base. Right? So this point here at the bottom of our height h is coplanar with the hexagonal base. And thus this segment that is the height would be perpendicular to that whole plane, even though it lands outside of the pyramid. Right? A right pyramid, the height will always be to the center of the base. A oblique pyramid will not be on the center. It could still be inside of it, or if it's very slanted, it'll land outside. All right, let's take a look at a few example naming exercises here. Name each of the pyramids or prisms shown in 249. Give as complete a description as possible. It's not enough to just say, it's got a pointy bit. Must be a pyramid. What kind of pyramid? We have a pentagonal base, so it must be a pentagonal pyramid. Okay? It looks like this height, if I drop down, lands outside of the pentagon, so it is not a right pyramid. This triangle does not look isosceles, right? This front-facing triangle here. No more evidence that it is an oblique pentagonal pyramid. This has a square, and we would expect its opposite to also be a matching square. So this would be a square rectangular prism, a square right prism. Okay. Here we have trapezoid there. The rest of them are rectangles. So it would be a right trapezoidal prism. Okay. So there we have the, there's the answers. Oblique, regular, pentagonal pyramid. Oh, I'm sorry. Yes, a regular pentagon. So regular pentagonal pyramid. I forgot the regular. Right square prism. Right trapezoidal prism. Okay. The bases are not the bottom of the prism. Okay. The bases are always the two matching sides. Okay. Notice two matching parallel sides. This rectangle is smaller than that one. They don't match. This rectangle and that rectangle are slanted. If you extend those planes out, they're going to run into each other. They're not parallel. So only the trapezoids could be the bases. And then equilateral triangle pyramid, a right regular triangular pyramid. Or you could say a right equilateral triangular pyramid. All right. Just like we had regular polygons, there is a set of regular polyhedra. Polyhedra that have regular polygons as faces form a group of especially interesting figures. The Greeks studied the regular polyhedra and imbued them with special significance. Right? Went on to all kinds of theories about the structure of the universe being based on these and such, and assigning each of them one of the four basic elements. The fifth then being ether, the space, cosmos. So, a regular polyhedron is a polyhedron in which all faces are regular polygons of exactly the same size and shape. Okay? Not just any set of, well, it has all regular, but it's all the same regular polygon. Okay? The Greeks discovered early on that only 5 such regular polyhedra can exist. Those 5 are shown here in the figure. We have the tetrahedron, the cube, the octahedron, 8 sides, icosahedron, my favorite, the 20-sider, and the dodecahedron, do 2, deca 10, 12-sided. And I have a set of 3-dimensional versions here. So let's go to zoom the camera in. Moment. Right. Here is the 4-sider and 6 and 8. Okay. See that one there. 12, and yes, all the faces are numbered because these are polyhedral dice. Okay, and there's the icosahedron, the 20-sider. Okay, very pretty looking. All right. Table 2.2 summarizes information about the regular polyhedra. This is good info, all right? This is some good stuff. Add this to your notes. Some interesting features here, right? The relationship between the number of faces, the number of vertices, and the number of edges in each one. So we count up faces, and notice what happens with the vertices. Okay, the tetrahedron matches the hexahedron and octahedron, aka cube and octahedron. Notice the faces and vertices switch. Same with the dodecahedron and icosahedron. The faces and the vertices swap. In fact, you can take one and connect the points inside of the other. If I took this cube, right? If you connected the points, took the center point of that face and connected it with a line segment to the center of each other face, okay? You connected all the adjacent faces together, those line segments would form the edges of an octahedron. Same with the octahedron. If you connected the center of each face of the octahedron with a line segment, you would outline then a hexahedron, and vice versa. That's why these switch back and forth. And you get the matching number of edges, 12, 12, and 30, and 30. Okay. If you examine the last 3 columns in the table, you might notice a pattern in the numbers. Mathematician Leonhard Euler, German, noticed a pattern in the relationship among f, v, and e. He observed that in every case, f plus v equals e plus 2. This relationship has become known as Euler's formula, and it holds for all polyhedra, not just the regular polyhedra. You can verify yourself that Euler's formula holds for the shapes in figure 250. I'm almost certain there will be an exercise in this section asking you to verify the formula for other polyhedrons. Here's another example of a polyhedron. You could check the Euler formula of this one if you wanted. The soccer ball. At first glance, it might appear that a soccer ball is an example of a regular polyhedron because all its faces are regular polygons, right? We have regular hexagons and regular pentagons here. But why is it not a regular polyhedron? Well, the faces of a soccer ball are regular pentagons and regular hexagons, thus not a regular polyhedron because its faces are not all identical. You've got 2 different shapes going on there, not regular. Okay. Interesting point of fact, the soccer ball design here is in fact exactly identical to the buckyball that we looked at the end of the previous section. If the faces of a soccer ball were all identical regular pentagons, the ball would take on the shape of a dodecahedron. It would not be sufficiently round, enough to roll like a ball. If the faces were all identical regular hexagons, the ball would be a flat surface, because as we saw In section 2.3, regular hexagons tessellate the plane. Turns out any true tessellation of the plane cannot immediately be like curled up and turned into some approximation of a sphere. You can't just make a 3D shape out of that. Flat is stuck, flat. So the arrangement of faces on the soccer ball does make it an example of a semi-regular polyhedron. A semi-regular polyhedron has several different regular polygons as faces, but the same arrangement of polygons appears at each vertex. So this is the same as our definition for tessellation, right? Or at least what qualifies a tessellation as a semi-regular tessellation. So that you're still using all regular polygons, okay? But at each vertex, you always have this same polygons meeting up. So at any intersection of line segments here, I have 2 hexagons and a pentagon. Here, 2 hexagons and a pentagon. Here, 2 hexagons and a pentagon. Here, 2 hexagons and a pentagon, right? Anywhere you look at it, it's always 2 hexagons and a pentagon meeting up. Thus, it is semi-regular. Okay, now on to the round ones. Cylinder. There are common 3-dimensional curved shapes analogous to the prism and pyramid. A circular cylinder is the shape formed by 2 identical circular regions in parallel planes together, with the surface formed by line segments joining corresponding points of the 2 circles. Line segments? Well, remember with our prism, we got to connect the edges of our 2 bases with a full rectangle. Okay? Since a cylinder, right, consists of 2 circular bases, it has no sides of the circular face. Instead, is an infinite number of points evenly spaced from the center. That's the definition of circle, right? And so you must connect all of those infinite points with an infinite set of line segments. Okay? So you have no flat surface around here, but you said that this nice round body of the cylinder. We gotta highlight that. Circular cylinder. That's not the highlighter. Parallel planes together with the surface formed by line segments joining corresponding points. Okay? 2 circular regions are called the bases of the cylinder. When the line segments joining corresponding points of the 2 bases are perpendicular to the planes containing the bases, the cylinder is called a right circular cylinder. Otherwise, it's an oblique circular cylinder. And as before, the height of the cylinder is the perpendicular distance. So if it's a right cylinder, the height is already perpendicular. If it's oblique, the height is perpendicular, but the connecting line segments are not. And of course, we have the cone. So a circular cone is a shape formed, highlighter please, formed by a circular region called the base, together with the surface formed when the apex, which is a point not in the same plane as the base, is joined by line segments to every point on the circle. Okay? So we have to set it as a circle and a point somewhere outside the circle's own plane, so they are non-coplanar, and then you connect that point to every point on the circle. You fill in all those line segments, you get a cone. It can be right or oblique. A right circular cone with its apex on the line that is perpendicular to the base at its center. Otherwise, it is oblique. In the right circular cone, the perpendicular distance from apex to center is called the height. So perpendicular distance is the height. For a right circular cone, the distance from apex to a point on the edge is called the slant height. Okay, so notice the difference there. Just like the pyramid, the true height is, right, if I wanted to, where's my cone? Here we go. Right, place the cone between my hands. Okay, how far apart are my hands? Right, that's the true height. The slant height is how far along the side, like if you wanted to, say if this was a building and you wanted to climb the side of it, how far are you walking up the side of the giant cone? All right. And lastly, we come to spheres. A sphere is the set of all points in space that are a fixed distance from a given point, the center of the sphere. So it is the exact 3D analogous to the circle, defined the same way. A line segment whose endpoints are the center and a point on the sphere is called a radius of the sphere, just like the circle. The length of any radius is called the radius of the sphere. A line segment that contains the center of the sphere and whose endpoints are on the sphere is called the diameter of the sphere, and the length of any diameter is called the diameter of the sphere. Just like with the circle. Okay? Radius goes from the center out to the edge. Diameter goes from edge to edge, but passing through the center. And we can give those measurements, and those measurements describe the measurement of the sphere itself. And I happen to have a 3D model of one here as well, but of course you could grab any marble or ball or bead, I'm sure, and get a nice sample of a sphere. So how about that takeout box? The shape of the container when it is folded up is called a frustum. Ooh, there's a good word. Frustum. Okay? And a frustum, you can almost think of it as a truncated pyramid. Okay? And truncated meaning we cut the top off. Okay? Nip the tip. Get a truncated pyramid forms a frustum. All right. It is actually more properly defined as two parallel, similar bases. Right. So you have one square that is large and then one square that is small, and you connect the edges like with any other prism. The top and bottom are rectangles, and the lateral faces are isosceles trapezoids now. So the frustum gets trapezoids for its lateral faces. So the shape of the box, when unfolded, ignoring extra flaps to secure the sides and the top, is as shown, where the rectangle for the top has been decomposed into two rectangles. So we took the fact that you would still have two lids. We didn't add extra flaps to hold them shut, but we still took it as two lids that open the side. So you have half the top here, half the top there, four sides, and the bottom. All right, and finally a bit of geometry all around us. A global positioning system, GPS. S does not stand for satellite. Global positioning system. Receiver works by determining its distance from each of at least 4 satellites. It uses a process called trilateration, which is a method of determining the relative position of objects. The GPS receiver uses the fact that it is located a certain distance from a satellite. We can think of the receiver as being located on the surface of an imaginary sphere that has its center at the satellite. 2 spheres intersect in a circle. 3 spheres intersect in 2 points, and 4 spheres will intersect in only 1 point. Thus, by using 4 satellites and 4 spheres, the GPS receiver can determine its exact location. Pretty neat, huh? All right, that's going to do it for this section. Thank you for reading along with me. So long, farewell, enjoy the rest of your day.